The first influence to roll stability we're going to discuss is dihedral. Dihedral is our largest contributor to roll stability, and dihedral is defined as the distance that or the angle that wings are rotated up relative to the horizontal. So if this would be an aircraft with no dihedral, and this would be an aircraft with positive dihedral. So unfortunately, the symbol that we use for dihedral is gamma, and gamma is also used to express the vorticity distribution on a wing, so that can be a little bit confusing. But we will, for this lecture, we'll only be looking at it in terms of dihedral. So that's what gamma means here. And so if you have positive dihedral, that means that your wings are rotated up. That means that the tip is higher than the root. You can also have negative dihedral. There are some aircraft that actually have wings rotated down like this. So this would be negative gamma. And you'll see that on usually aircraft that have larger fuselages and high wings. We'll talk about why that is later. But anyway, that is called anhedral. So up here is called dihedral if it's positive, and if your wings are rotated down, that's either called negative dihedral or anhedral. Okay, so let's talk about why dihedral works as an excellent contributor to roll stability. And to do that, I'm going to attempt to draw this aircraft at a bank angle. So this is our horizontal here, and we're at some bank angle phi. But now we're going to give those wings some dihedral. So the blue here is the actual wings, and they are at some positive dihedral gamma. Okay. So let's talk about what happens as this aircraft begins to side slip. So as we side slip, we're going to get some velocity here in this direction, and that side velocity we're going to call little v. Okay, so that would be 0 if we were in steady level flight, but now we're at some bank angle, and so we get some side slip velocity because our weight vector. Remember, our weight is acting towards the ground, and so now we have some component out the right wing, okay, with a positive bank angle. So we get some v, little v, and the component of that is perpendicular to the wing itself is little v times the sine of gamma, okay? So we have these two components. V is our side slip velocity, and then we've got V sine gamma that's actually perpendicular to that wing, okay? So little v is related to our side slip angle beta, and through a small angle approximation, that is roughly equal to our free stream velocity, capital B, times beta, okay? That's using a small angle approximation. So that means that V times sine of gamma is equal to V times beta times sine of gamma, okay? So now let's look at an angle of attack alpha, or a change in angle of attack. So for that, this V sine gamma that we have right here is actually our change in that vertical velocity that's going to be seen by the wing, and through the small angle approximation, that vertical velocity, we'd take that vertical velocity, which is V sine gamma, and divide it by capital V in order to get a change in angle of attack that is that wing is seeing, or the local airfoil sections along that wing are seeing. Okay, so that delta alpha is little v sine gamma over to capital V, and that is through using a small angle approximation. And so if we plug this guy in for the numerator there, we find that this just comes out to be beta times sine gamma. Okay, so on the right-hand side of this aircraft, we're going to have our delta alpha over here is equal to beta sine gamma. And actually, on the left-hand side, our delta alpha over here is equal to negative beta sine gamma. Okay, so what we see is that on the right-hand side, we actually have an increase in angle of attack. And on the left-hand side, we have a decrease in angle of attack that is seen by the wing. And so with that increase in angle of attack, we have an increase in lift on the left-hand side, or excuse me, on the right-hand side, and we have a decrease in lift on the left-hand side. And so that creates, that difference in lift between the right and the left-hand side creates a rolling moment. In fact, it creates a negative rolling moment for a positive side slip. Okay, so that's exactly what we want. We want CL comma beta to be less than 0. And that's what we get. With a positive beta, we get a negative rolling moment. So the change of rolling moment with respect to beta is negative. Okay, so that's how dihedral is used to create a rolling moment. Now, dihedral is one of the largest contributors to rolling moment or change in rolling moment with respect to beta. And so, so much so that roll stability is sometimes called dihedral effect. Okay, so we're talking about roll stability. And some people will actually use these phrases interchangeably, roll stability and dihedral effect, because dihedral is such a dominant effect on roll stability. And so this is used on many, many aircraft to control the roll stability, and so people will just call it dihedral effect. Now, one of the attractive things about using dihedral to control your roll stability is the fact that dihedral doesn't tend to alter the lift distribution very significantly for small angles, right? So if this is the lift distribution on a wing with 0 dihedral, and then you add in just a little bit of dihedral here, the lift distribution actually doesn't change significantly due to that dihedral. And so that's one of the benefits of using dihedral. It can be, actually, you can go ahead and design a lot of the aircraft and place your engines and nacelles and fuselage and figure out if you're going to use a high wing or a low wing. And we're going to be talking about the influence of these different things. And then basically find out, how much roll stability do I have on this aircraft? And then you can go back and correct it for how much roll stability you want by simply changing the dihedral on the main wing. And it's not going to impact or significantly impact the other design decisions that you've made because the aerodynamics are not significantly impacted by dihedral. So that makes it kind of an attractive choice that can be used later on in the aircraft design process to give you the roll stability that you're really looking for. Now, one other thing that I want to point out here is that if we use a small angle approximation here, then our delta alpha is basically equal to beta times gamma. So this is using a small angle for the dihedral angle. So for small dihedral angles, our change in angle of attack on the left hand and right hand sides of the aircraft are basically directly proportional to gamma. Okay, and we know that that the lift is so let me just write this out. So delta alpha is basically proportional to gamma, and we know that lift, our delta lift on each side, is proportional to our change in alpha, and we also can say that our rolling moment is basically proportional to the delta lift. So this is a really nice thing because these are basically all proportional to each other. That means for small dihedral angles, the change in rolling moment is basically proportional to gamma. So there's a kind of a linear relationship there. So if I want CL beta to go up by a factor of 2, then basically doubling that dihedral, if I already had some dihedral in the wing, then doubling that dihedral would get me very close to that what I need there. So anyway, that's just kind of something interesting for small dihedral angles.